So I just spoke to the folks sitting here at Aspire, right? And I mean at Actrack, and we said that what we're going to try and do is, we're going to leave the session very, very open, and we're going to make sure that we try and connect all the different concepts that you guys have heard about so far. Okay. And so what I will do is maybe without even you asking me this question, I will maybe start with the first set of slides around, or first topics around the whole testing framework and how it connects to type 1 error, type 2 error, sample size, all of those kinds of things. Yeah, I know Andrew spoke a little bit about that. I wasn't here for the full thing, but did he go into that in some level of detail, or hypothesis testing, type 1s, type 2s? Yes, everybody understands how that works? Yeah, so we can do it. Okay, all right, okay, fine. So let us just work on that, and let's see if that is something we can quickly run through. Yeah. Normally I would use a board to do this, because that's most convenient to me. But since that's not possible for us today, let's try with this. Okay, is that okay with everybody in the chat window? So in the meantime, as I was saying, what I would really like is for all of you to have your questions ready for me, to say, what do you really want me to focus on? Okay, I'll spend maybe 10-15 minutes on this whole, connecting the testing scenario to the sample size and p-values and all of those kinds of things, right? So we'll spend maybe 10 minutes doing that. And then after that, it's open season. Yeah, we'll open it up to whatever you want, and hopefully by then Sadhana will come and she'll start taking over the whole sample size bit. Sounds good? All right, super. So let us see. So simple stuff, right? We'll start with different types of data. I think you guys spoke about this. Overall, we have categorical, we have quantitative, right? Within categorical, you have the different kinds. You have binary, you have nominal, you have ordinal, yeah. And I think we spoke about this. And quantitative, you have discrete and continuous. Okay. Examples of binary data. Yes or no? Yes. Dead, alive. Male, female. Binary. Yes. Sure. Exactly. Yeah. The whole movement is towards non-binary data, non-binary gender now, right? So yeah, by gender, I think is that's why you don't see it written there. Okay. Because I made sure I took it out, because it's a political landmine now. Yeah. So we don't know about gender. Yeah. Is it ordinal? Okay, good. So at least it's not ordinal for sure, right? And we're not sure whether it's binary, so we'll call it nominal for now. Okay. All right. But the others are relatively non-controversial. Yeah. You know what nominals are. Okay. And then you know what ordinals are. So especially in cancer, you have staging of the disease. All of those kinds of things are ordinal, right? In nominal, you have all the different kinds of blood types. You have maybe the tumor site, primary tumor site. All of those kinds of things are nominal, right? And then binary is anything which is yes or no. Response rate, yes or no, and so on and so forth. Yeah. Then you have in quantity of discrete and continuous. So what is discrete? What is continuous? Really tough question, no? I know, but it's so hard, no? So for example, if you think about age, they are whole numbers, but are they really discrete? Not really, right? I mean, you don't think of them as discrete, correct? You kind of think of them as continuous, even though they're all whole numbers. Yeah. So the idea is that discrete and continuous, in a way, has something to do with the range. If the range is very high, then you kind of think about it as continuous. If the range is relatively narrow, then you think about it as discrete. It doesn't really matter too much, because the way you analyze the data is the same. That's the beauty, right? So you don't have to worry too much about it. Okay. It's not exactly the same. For example, if you say number of episodes, you don't expect that to have a huge range. Let's say you're talking about migraine, and it's a number of episodes of migraine. So it's either 0 or 1 or 2 or 3 or 4, right? Something like that. Yeah? So that you still think about it as discrete. And the main reason you try to make a difference between discrete and continuous, all of these different types, is because these have a huge impact on how you analyze the data later on. Okay. And you don't want to mess things up. So for example, you don't want to think about, you want to think about a variable as discrete if the intermediate values don't make any sense. Okay, so for example, let us say you have number of migraine episodes and you say I have 2.5 episodes. That doesn't make sense. You can either have 2 episodes or you can have 3 episodes, right? So the intermediate values don't make sense. Whereas age, the intermediate values make sense. Yeah. So you can say I'm 30 years old or I'm 30.5 years old. It actually makes sense. So if the intermediate values start to make sense, you think about them as continuous. If the intermediate values don't make any sense, you think about them as discrete. Okay, and then the way you analyze them is slightly different. Make sense? Okay, so that's the only major thing that I wanted to do, because you guys know this stuff really well, right? Obviously, you're talking about much more advanced things, but just for you to know, this is what we're talking about. Okay, good, super. All right. So, I mean, this is an example, so forget about that. I mean, this doesn't make any sense. That's the only slide I needed from them. Sorry. Okay, we'll go to the next presentation. Yeah, no, it's perfect. Right. So how do we describe this data, right? So, when you have quantitative, if you have categorical data, it's simple enough. You're just going to do percentages, right? So you're going to do percentages, proportions, ratios, all of that good stuff. When you have numerical data, you're going to think about it in three different ways. You have a center and location, right? So you're going to talk about mean, median, mode, and so on, right? Mode, I mean, it's good to see it on the screen. Do you ever use a mode? As far as I know, never. Yeah. Okay. You do use it for other things, not in our. I mean, you use it when you go buy shirts at Shoppers Stop. There they'll put a mode. They use a mode to pick out which, size of shirts they want to stock, right? But otherwise, in our kind of thing, you don't really use a mode much. You have other measures of location like percentiles and quartiles. You have variation, and the things that we really care about are the variance of the standard deviation, and you kind of know what those are. Yeah. Okay. This is a little bit about the shape of the data, right? So you know this as well. You know that you have left skewed data, you have symmetric data, you have right skewed data. Examples of left skewed data. Okay, examples of symmetric data. Sorry? Yes, distribution of blood count. Blood pressure, fine. Fair enough. Distribution of blood pressure in normal population. Yes. Good example of symmetric data. What about left skewed? So left skewed is typically, what does it mean from the chart? It basically says that you have a small number of counts IQ. So you think there are very few people with very low IQ and a lot of people with very high IQ, or middling IQ. So you have a few people with very low IQ. You have most of the people on the right side, and then a very few people with extremely high IQ. It could be, I've never looked at the distribution of IQ, but I'll trust you on that. What is an example of right skewed data? Age, interesting. Yeah, but not so much also. I think possibly, yeah. I agree. If you compare to the Western world, I agree. But from our kind of areas, from medical field, what is an example of right skewed data? Absolutely, anything to do with the half-life of drugs, yeah, anything to do with lab values, anything that has that. So you see most of the people with lab values, very few with low, most of them in a with a particular lab value, and then a few of them with very, very high values, right? WBC counts, all of those kinds of things, correct? So that's so a lot of the data that we actually deal with is actually right skewed data. Yeah, fair enough. Okay, good. So then, yeah, we won't worry about all of these things. These are some formulae. Yeah, good. So what I want to now move into is things called what is a population and sample, and why do we have a problem with hypothesis testing, right? So what is the concept of a population? What is a population? A population is the entire set of people that we are interested in, right? So all women who have a BRCA gene, all women who have breast cancer, All men, all people who have a particular kind of cancer, right? That is our population of interest, whatever it may be. It doesn't have to be all. Okay, you can choose to say, I am looking at people with stage 3 cancers in India. That's fine. Or you may choose to say people with stage 3 cancers in Mumbai. Okay, or you may choose to say people with stage 3 cancers who come to Tata Memorial. Whatever your population is. Okay, you define what your population is. Okay, of interest. The narrower your population is, the less generalizable your results are. Clear enough? Yeah, that should be simple. Okay, so if you look at your population being all patients who come to Tata Memorial, that is going to be a narrow population set. Yeah. Okay, so whatever you see there is going to be non-generalizable. Okay, so you have that about population. Now, what is a sample? Yeah, a sample is a subset of the population. Correct. Now, the question is that how good your sample is based on how you define your population. Correct. So, if you say your population is all cancer patients in India, okay, and you look at your sample only at Tata Memorial, then there is a problem. Yeah, because your sample is not necessarily representative of your population. So you may not be able to make the right claims unless you say that Tata Memorial is really representative of all the cancer patients that you see anywhere in the country. Yeah. So your sample will depend on how you define your population. Okay. If you say all cancer patients in the world and you do the study only at ACTREC, then there is a problem again with that. Yeah, because it won't be generalizable. Does that make sense? Of the population. Okay. So the whole idea of hypothesis testing is our ability or our need or a desire to make a statement about the population based on the sample that we collect. So every clinical trial that we conduct is a sample. Yeah. So most of the time, what is our sample? It's just the one sample that we get, right? The one clinical trial that we conduct. Okay. But all the hypothesis testing framework is based on repetition of those samples over and over again. That's what everything is based on. Yeah, so which means that there is always inherently going to be a problem because we are trying to make a statement about a population based from a sample. Okay, and that's where there is a likely chance that we're going to make an error. Now, how will we make an error? We'll look at it. Now, how do you define our hypothesis? And I'm hoping that this is something that you're going to be working on today or have already worked on. The question is drug A more effective than drug B? Okay, in treating, let's say, type A, whatever type of cancer. Okay, that's a question of interest. Is that a good enough hypothesis? No, it's not, because it's not very specific. Right? So you're going to say, how is drug A more effective than drug B? Correct? So let's take cancer, right? I mean, we're all in the oncology space. Let's take that as an example. What are the different ways in which drug A can be more effective than drug B? Response rate, PFS, OS, quality of life, less toxicity. So maybe quality of life, maybe. Yeah. What else? Tumor shrinkage, size of tumors. Yeah. All of those, right? Now think about it. So the idea here is the reason why we talked about types of variables before was because if you say that I'm going to look at tumor shrinkage, what kind of an endpoint is that? Sorry? Right, and you look at the volume of a tumor, right? You're looking at longest diameters, and then you're looking at the volume of a tumor. Right? So that is dependent on, that is a continuous variable. Okay. The next question that you have is, let us look at response rate. So what are you looking at? Did the patient respond, yes or no? Okay. What kind of a variable is that? Binary. Look at progression-free survival. Time to a particular event happening. It is continuous, but it's a very special kind of a continuous variable because it is skewed, right? Skewed. Okay. Or let's see. We have a whole bunch of patients who can have an event right now, Okay, so you will see that the median survival in 6 months, you will see most of the patients, having an event between 3 and 9 months, but then you will see a few stragglers, a few patients who don't have an event at all for 9 years. Right? So it's right skew data. There's a kind of event data. Completely different kind of data. So the kind of data type that you have will make a huge difference in your analysis and your sample size calculation and everything else. Make sense? That's why that is important. Okay. All right. So how do you want to categorize this? You say basically that response rate after 4 months, okay, with drug A is less than or equal to response rate after 4 months with drug B. It's a very specific question. Look at response rate at a particular time, okay, and so on. Now, once you write this as a hypothesis, if you don't see a difference in 4 months, but you see a difference in 6 months, then you can't go back to a statistician and say, hey, do something, please. Huh? Can you make that 4-6 months, please? Huh? Can you do trend? Yeah, you can't do all of these things. Okay. So the idea here is, if it is 4 months, that is what your hypothesis is stating, then that's what it is going to be. Okay. If you're not sure that it is 4 months or 6 months or 8 months, okay, then you go in and say, give me my best overall response in 9 months, within the first 9 months or first year. Okay, so you go to a statistician and confess all the things that you don't know about, so that they will be able to formulate the right hypothesis for you, help you to formulate the right hypothesis. Make sense? Okay, that is critically important, because once you write a hypothesis, that's what you're going to base your analysis and your sample size on. Okay, and you know about null and alternatives, so I'm not going to spend time on that. Right? Null is what you want to discard, alternatives what you really believe. Okay, sounds good. And so what is the hypothesis test? It's a decision rule. Okay, so you have all your data that you collect. Okay, you put it in this mixer, cement mixer. Okay, and out comes a decision that says, yes, reject H0, accept H0 by magic. Okay, so forget about this. All right, and therefore you see these errors. Okay, so what are the errors? Essentially, let's say these are, suddenly you become God. Okay, and you're able to treat every patient with drug A in the population. Okay, and what you see, those blues, no, they are your responders, and your oranges are your non-responders. Okay, so now you're able to see, so you take the entire population and treat them with drug A. Okay, and these are the number of responders and non-responders you see. Okay, now, so you get an 80% response rate. Okay, now what happens is you go to an alternate universe. Okay, because everything in Marvel now is about multiverses, right? So you can go to a multi-universe, right? So go to an alternate universe, okay, and there treat all these same patients with drug B. Okay, and you see what the response rate with drug B is. All right. So now this is your drug A and drug B. These are your full population. And drug A response rate is 80%, drug B is 35%. Obviously, drug A is better than drug B. Simple. This is easy to do, no error at all. Fantastic if you can treat every patient in the population. Okay, now what happens if these are your samples? So what you see non-shaded are your samples. Okay. And now in drug A, you have 5 out of 9 responders. And drug B also you have 5 out of 9 responders. Okay, you just were really, really unlucky because you picked all the responders in drug A and drug B and all the non-responders in drug A. Okay. And so therefore you see that both are 56% and you say, drug A is the same as drug B. Correct? So this problem of an error happens because you're trying to make a decision about your population from your sample. Simple enough. Okay. So what are the different types of errors that you can make? Is the truth is that there is no difference, but you say there is a difference, or the opposite is the truth is that there is a difference, but you say there is no difference. Okay. So type 1 error and type 2 error. Okay. Simple enough. I don't think I want to belabor the point here. Everybody understands this? Yes? Okay, good. Okay. And the opposite of that, so basically probability of type 1 error is called alpha, probability of type 2 error is called beta, 1 minus alpha is called your confidence level, 1 minus beta is called your power. All right. So basically what you start to say is, type 1 error is the risk of rejecting of approving an ineffective drug. Type 2 error is the risk of rejecting an effective drug. Which is more important? Type 1 error. So all of you are doctors, you are okay with good drugs won't come to the market. Huh? No, you are, no. So they both are important, correct? Now the problem is they're important to different sets of people. Yeah. So regulators are saying, I don't want a drug in the market which is ineffective. Patients say, I don't want to take a drug which I think is ineffective. I mean, which I think is effective, it actually is ineffective. Okay. So for them, type 1 error becomes more important. So you try to control that. You say 5%, 1%, you're very strict about it. Okay. Type 2 error is also important to the regulators and to the patients, right? Because they're saying, hey, there is a drug which works, but you're not putting it in because you make a mistake. It's still important. It is more important to the companies as well. Okay, so they say type 1 is regulators risk, type 2 is sponsors risk, and all of that kind of things. But the fact of the matter is, they both are important. Okay. Now, this is where I want you to focus a little bit because you're trying to make this connection between all these different things. Okay. What you see in the blue line, the blue chart, okay, that is your distribution of your test statistic under the null hypothesis. Now, what is a test statistic? Is something that you see from the population or from the sample. That is your test statistic. Okay. All right. So we didn't get into the details of how you form a test statistic. You know, if you had a little bit more time and I could use a board, we could have done that. It would have been fun, but you know, we can't. So let's assume. Let us say that I want to make a statement about the population response rate. Okay. So my population response rate is what is the proportion of responders in drug A versus drug B. Okay. So what do? I look for a sample from both of these. And in the sample, I look for a sample response rate for drug A and a sample response rate for drug B. Okay. What is the population response rate called? It is denoted by a symbol. What symbol could it be? It's denoted by a symbol called pi. Not the eating pie. The symbol pi. Okay. What is the sample response rate typically called as? The English equivalent, which is P. Okay. So remember this always, guys. Okay. Whenever you read a paper, okay, and you come across a Greek alphabet, is to deal with the population. Okay. The population mean is called mu. Okay. The sample mean is called X bar. The population mean is called, variance is called sigma. Okay. The sample variance is called S, the English equivalent. The population variation proportion is called pi. The sample proportion is called P. Okay. So every time you see a Greek letter, it's a population. Every time you see an English letter, it is the sample. This comes from the sample. Okay. So you want to figure out. So let us say that this is a continuous variable. Okay. Size of the tumor. Okay. So you want to figure out what is the population. Okay. So you see this particular blue thing. Okay. That is the distribution of the test statistic of the sample, okay, under the null hypothesis. Okay. So you're essentially saying that there is no treatment effect. Okay. All right. This purple thing that you see here. Okay. This is your distribution under the alternative, which means that there is a difference between drug A and drug B. Okay. So, and these are your observed values down below. Okay. So now if these observed values are in this space, then it's easy, right? What are you going to assume? What are you going to conclude? You're going to conclude that drug A is better than drug B. You're going to reject the null hypothesis. Okay. If your observed values are here, then what are you going to conclude? Accept the null hypothesis that drug A and drug B are the same. Okay. Now what happens if it is somewhere over here? Then you don't know, no, because it could either of them could be true. Drug A could be better than drug B, or drug B could be better than drug A. Right? So how do I make a decision? Okay. The way I make a decision is that I draw this line that you see. So I draw this line and I say anything to the right of this line, okay, here, anything to the right of this line is the decision that I'm going to reject my null hypothesis. Okay, anything to the left of this line, I'm going to accept the null hypothesis. Sounds good? Fantastic. Now, how do I draw this line? No, because data is here. Data is below. So you can't do it on data. No, you can't do that also. That you can't do. You make a decision, but how do you know? So, I mean, for example, why would I draw this line here and not here or here? Like, how do I pick this spot to draw this line? The statistic is at the bottom. Yeah. So we are saying if the statistic falls to the right of the line, I will make a decision, or left of the line, I'll make a decision. Correct? But how do I draw the line itself? The line can't be based on the statistic. You have chosen the line, but how? Excellent. Yes. So you choose the line based on your alpha and beta. And this is how you choose the line. Okay. Because anything that you see here in this part of the graph, right, this red part, is what? So now your decision, because it is to the right of the line. So what is your decision? Your decision is that you're rejecting the null. Okay. But it is under what distribution? It is under distribution that it is the null. The null is true. So you're rejecting the null when in fact the null is true. Right? So what is this red area supposed to be? Exactly. It is a probability of rejecting the null when your null is true. Okay. And that is alpha. Okay. When it is a left here, if you take this orange, part, okay, you're not rejecting the null, you're accepting the null when in fact the alternative is true. So that is your type 2 error. Okay. So you fix your type 1 and type 2 error. So you start off with your study and say, hey, I'm going to fix my type 1 and type 2 error. Okay. So if I fix my type 1 and type 2 error, then I should be able to draw this line. As long as I know what this treatment effect is. This blue difference here, 5. This is your treatment effect. As long as I know what my treatment effect is. Okay. If my treatment effect was very wide, okay, what if my left line was like this and my right line was like this? Okay. Then the overlap between these two lines is very low. Yeah. When that happens, when that overlap is very low, then my type 1 and type 2 error can be very small. Okay, so I can easily accept or reject a null based on a very small sample size, or very easily I'll be able to make that difference. My chance of making an error is going to be very small. Okay, if these are very, very close, these two lines are very, very close, these two curves, then the chance of making an error becomes much higher, right? So now if they are very close, how can I still make my type 1 and type 2 error small? Exactly. Perfect answer. Larger sample size. What happens when you do a larger sample size? No, what happens to these curves? Correct. What happens to these curves is these curves become thinner and taller. Okay. So this curve now becomes like this. Okay. This other curve becomes like this. Because as my sample size increases, my variability decreases. So the curves become thinner. So I can still control my type 1 and type 2 error, alpha and beta. Okay. This is a relationship that you have between testing, type 1, type 2 error, sample size, treatment effect. Clear? Questions, anybody? No? Yeah. So this is how you construct a test, right? And Sadhana is going to come and tell you. So because of this, what happens is that you start to say, I'm going to fix my type 1 error. I'm going to fix my type 2 error. I'm already going to fix my treatment effect. I know what my treatment effect is. And as doctors, you should be able to go and say, I know what my treatment effect is. If these 3 things you know, then Sadhana will say, simple. Here is a formula. I can give you a sample size easily. Okay, no problems. Yeah? The issue is that you say that actually I don't like that sample size number. Okay. So now can you please change your alpha and beta? So how will I change alpha and beta? It's up to you. You have to tell how much error you are willing to take. Okay, you can't do anything about treatment effect. You can't suddenly say actually the drug is only so effective, but for this study, let me assume it's more effective. You can't do that either, right? Okay, but you have to play with these 4 things only: treatment effect, alpha, beta, sample size. Okay, and mostly you play with 3 things to come to the sample size. That is called adaptive designs. No, it is not. Okay, but that is how we use adaptive designs. Okay, can I start with this alpha, beta? Oh, I don't like the sample size. Can I change my alpha and beta? So you adapt a design based on the sample size number that you like. Okay, that's not how it's supposed to be. Sounds good? Okay, all right. So then let us just quickly say what is the p-value? Okay, because it's important. Okay, so what is a p-value? A p-value is basically, we go back to that. It's not a probability value. Whoever said probability value, not correct. Okay, what is a p-value? A p-value is the probability of seeing a test statistic, an observed value, as extreme or more extreme. Okay, so for example, if your observed value is here, okay, this line, then your p-value is all this area to the right of this line. Okay, all right. If your observed value is here, then your p-value is all of this area to the right of this line. Make sense? Okay. Therefore, as long as your observed value is to the right of this line, yeah, what will that area be? It will always be less than 0.05. No, because this is 0.05. Correct? So as long as your observed value is to the right of this line, your p-value is always going to be less than 0.05. That is why, what do? You look at a p-value and say, oh, it is less than 0.05, I will reject. Okay, that's the yin and yang of it. Okay, if your observed value is here, then what is your p-value? It is all this area, right? This whole area, and that area is bigger than only this area, correct? And therefore your p-value now is larger than 0.05. So if your p-value is larger than 0.05, you do not reject the null hypothesis. If a p-value is greater than less than 0.05, you reject the null hypothesis. Okay, simple. This is the whole construct of testing. Okay? Once you understand this, then everything else is easy. Okay, if you have continuous variables that are normally distributed, then it will look like these kinds of curves. Okay, if you have other kinds of variables, if you have a binomial variable, then it will look like 1 and 0. It will look like a discrete value, but it's the same concept. Okay, if you have time to event, then it will be a skewed data, but same concept. Okay, so the concepts all remain exactly the same. Yeah, it's just easy to see in symmetric, but if it is not, if it's a different kind of variable. So if you had ordinary binary data, okay, then you would do logistic regression. Yeah, you do exactly the same thing. Okay, if you had time to event data, then you would do survival analysis. You do Kaplan-Meier, Cox proportional analysis regression. Again, same concept. Clear? Okay, so I'm going to stop there. Okay, unless there are other questions. Sadhana, I know you have to come in and do your thing now, no? But maybe you stop and see if there are a few questions. One-sided and two-sided alpha. See, you asked a question, so it's actually in a way. Yeah, sure. Thank you. Perfect. So with one-sided and two-sided, no, it's actually not that complicated. You know, I mean, it's a. Let me phrase it this way. It is a decision that you have to take. Okay, but it is not that big a decision. Okay? So let's think about it. What do I mean by that? When you start off with saying, I want to test drug A and drug B, Okay, you want to start off saying that I am going to always do this because I think drug A is better than drug B, right? You're never going to come in and say, actually, I have no idea about drug A and drug B. Maybe it is better, maybe it is worse. So I'll do a two-sided test. No, you always start off saying you know that drug A is better than drug B. Okay. So will somebody stop you from doing a one-sided test? No. But all the regulators are coming back and saying is that the error that you can make is on both directions. And we want the error to be equally split in both the directions. So if you want to do a one-sided test, all for it, go for it. But just do it at 2.5% alpha. Okay. Otherwise, do a two-sided test at 5% alpha. It's the same thing. Won't matter. Okay. So that's the whole thing. So it is about how you want to phrase your question. Okay. We sometimes get into semantics and make it a little too complicated. But most of the time, the answer is fairly simple. Is you want to do a one-sided test, no problem. Do a one-sided test. Okay. But do it at 2.5% alpha. Nobody will have a problem. If you want to do a one-sided test at 5% alpha, then there is a completely different thing. You have to be able to show somehow that there is absolutely no way that in your sample also the drug can be worse. And there is no way to show that. You know, population-wise, the drug cannot be worse. That's fine. But what stops you from getting a really bad sample where it goes in the opposite direction? And that's why it is much harder to sell a one-sided test at 5%. So non-inferiority study is slightly different. Okay, a non-inferiority study, what you say is your hypotheses are flipped. Okay, so in a non-inferiority study, your alternative is that the drug A is surely inferior, which means it is less than. Okay, and the one that you want to reject is that it is equivalent or non-inferior. So the way you set up your hypothesis itself makes it one-sided. Okay, because that takes up the whole space of the decision matrix that you have. So in those cases, it is perfectly okay to do it. Yeah. You could, but I think that, you know, I mean, you would have, it depends on the non-inferiority margin that you. The non-inferiority margin is something where, so what the regulators come and say is that they want to have a high level of confidence, right? So you can either do that by using a conservative margin, okay, in which case if you go back and say, I'm using a super conservative margin, and so therefore I will set it up as a one-sided test, I think that'll be fine. Yeah, so then it becomes a question of a treatment effect. So again, it boils down to these set of three things only. Treatment effect, alpha, beta. It could, but that's okay. Because the way you're setting a hypothesis is that drug A is less than drug B, and the other way is that drug A is greater than or equal to drug B. Right? Correct. So you can. No. So and Sadhna said she's not going to get into it, but we will get into it. Okay. Which is you do it as something called hierarchical testing. So you can't do it automatically. Okay. So I have to talk. So should I talk about multiplicity? I don't know how much time I have. That's the problem. Should we talk about multiplicity or? Sorry? Martin has covered. Okay, we'll talk a little bit about multiplicity. Okay. So the way this happens is if you are testing for non-inferiority, you're saying that my drug is not inferior to the other drug. Okay, and you're able to prove that it is not inferior to the other drug, then you actually can do a subsequent test for superiority for free. Okay, buy one get one free. Yeah, so you can do that, and you can say that now I will test for superiority without spending any alpha. Now, what is this whole concept of alpha spending? So we talked about multiplicity, no? So let's take this example. Okay, 5 minutes on multiplicity. Okay? Let us say that you have one rope. Okay, and in that rope there are knots. Okay, and the probability of each knot breaking is 5%. Okay, so somebody gives you this rope and says you have a choice between rope 1, which has 1 knot, and rope 2, which has 4 knots. But you have to use this rope to climb a very tall mountain. And if the knot breaks, you're dead. Which rope would you like to have? The 1 knot, right? Because the chance of one of those 4 knots breaking is much higher than the chance of 1 knot breaking. Okay. Same concept is what we use in multiplicity testing. Okay. I'm doing one test at 5% alpha. I'm doing another test at 5% alpha. Okay. Now we say that the overall chance of making an error is what? Close to 10%. It's not exactly some mathematical calculation, it's close to 10%, right? And as the number of tests keeps on increasing, that chance of making an error and not breaking goes on increasing. Okay. So what is the way to fix it? Correct. Mathematical correction to the alpha itself, right? So what are you going to do? You're going to say that instead of doing each test at 5%, I'm going to do each test at 2.5%. Yeah. So now my overall error is still 5% for 2 tests. Okay. So instead of the not breaking probability being 5%, if the not is 2.5%, then whichever rope you choose. Makes sense? That's what we are doing. Just taking an alpha. While designing the study, absolutely. No. After nothing can happen. Whatever I must happen is at the beginning. Okay. So you say that I am going to now do each test at half the alpha. If I have 2 tests, I have 3 tests, then I do 1/3 the alpha. And so one way of doing it. Okay. What is the second way of doing it? Correct. So actually, no. So what you can say is that instead of doing 2.5, I will do 4 and 1, because one endpoint is more important to me than the other endpoint. Okay. So I'll do 4 and 1. I can do any kind of split. Experiment only. Whatever is important to the investigator. Okay. No. Up to the person. Yeah. Now the thing is that there is another way of doing this, which is, think about it this way. Supposing this rope had 2 knots. The second knot will break only if the first knot breaks. Okay. The second knot will not break by itself. The second knot will break only if the first knot breaks. It doesn't matter which rope you take. No, it doesn't, because in both cases the rope breaks. Those are called hierarchical testing procedures. That I will test my first endpoint, and if my first endpoint wins, if I am able to reject a null from my first endpoint, only then I will test my second endpoint. Otherwise, I'll not test my second endpoint at all. Okay, that's called a hierarchical testing procedure. Okay. No, same only. Buy one get one free. That is that scheme. Only for hierarchical. See, for example, what you're saying is that you have 2 knots in a rope. Okay. And you're going from the bottom. This is the first knot. The second knot will not break unless the first knot breaks. Okay. So now the overall error, overall probability of breaking is only 5%, right? Same way, a hierarchical procedure essentially says that first I'm going to test my first endpoint, whatever it is, my primary endpoint. Only if I reject the null hypothesis, okay, only then I will test my second endpoint. Not composite. They will be sequential, one after the other. So for example, I will say that first I want to test if my drug increases progression-free survival. And if it does, then I will check quality of life. Okay, if it does not increase progression-free survival, if it does not improve that, then I don't want it, then I don't care about quality of life. So it is a hierarchical endpoint. It is a secondary endpoint, sequential endpoint. Yeah. Because then you're cheating, no? Right, but you are now saying it is because you're saying that I can either have this one break or that one break in the beginning. That is not okay. Yeah, because as long as one of them breaks, the rope is going to fall down, right? Correct. So so that is cheating. So you can't do it afterwards. Okay, there is a way to do it afterwards. Okay, there is a way, but that is like, you know how when you go to buy bhaji, you buy bhaji, then they give you some kothmeer for free, no? Just like that. So secondary elements are like kothmeer. Okay, so they just give that to you. Okay, it is useless. You know, nobody cares. Okay. But the point is that nobody will care about kothmeer unless you buy the bhaji first. Okay. So the regulator will never approve your study if the primary endpoint is robust. Then they say, okay, do as many secondary as you want, their labels. It doesn't matter so much. No. Hierarchical is all for primary. Okay. So hierarchical are all for primaries. Huh? I'm sorry. Sorry, question? No, having in the initial part is the only way the sample size will be correct. Otherwise, you have to. Yeah. Yeah. Correct. Yes. Okay. Let's backtrack. Correct. Great question. I want you to tell me which kind of testing procedure you're comfortable with. Okay. Because as a statistician, the clinicians ask of me is always, how can I reduce my sample size? Right? So the ask I have back of you is, what do you want to do as part of the study? What is important to you? Okay, you are going to spend a lot of money and effort and time in doing this study. Obviously, you want as many results, outcomes out of it as possible. But how important are all those outcomes for you? Are they all equally important? In which case, I'll have to split my alpha and the size goes up. Or are you okay to say this is the most important thing? If I don't get this, the study is gone. Okay, then I will do the others. Correct. So the alpha is 5%. But then if you want 4 endpoints and 5%, then each of your alpha will become 0.0125%. Then the size of a study will go up, right? On the other hand, if you say endpoint 1 is what? Correct. Absolutely. Okay. So, but these are not only subgroups. Subgroups are different. Subgroups are saying, I now want to find out if it is different for males and females, for people with this particular gene or not. This biomarker positive, negative. Those are subgroups. Those are different. I am saying you're saying that I want to show that the drug increases my survival. Okay. Also is great for my response rate. Also does overall survival. Also does quality of life. Correct. Yeah. They are not co-primary. If they are that is my question to you. If they are co-primary, then they're all equally important. Then you will have to give me alpha. Okay. But if you come back and tell me they're not all equally important to me, okay, I will do endpoint 1. And if endpoint 1 I win on, then I will do endpoint 2. Otherwise, I don't care about endpoint 2. Okay. Then I will say, okay, then I'll give it to you with same alpha. Then I'll give you that extra kothmeer. Right? One second. Let's just finish. That is only if they are co-primary, right? So only if you tell me that I want to win on any of these, I want to do one study. At the end of one study, I want to say at least the progression-free survival is good, or the overall survival is good, or quality of life is good. Okay, then I will say what are the effect sizes for each of these. For progression-free survival, you need 100 patients. For overall survival, you need 200. For quality of life, you need 250. You have to do a study with 250 if you want to win on something. Okay. On the other hand, if you come to me and say that, boss, I want You just, my primary thing is progression-free survival. Okay. If I get that, then I'll consider my study to be successful. Then I will chumma try for overall survival. Okay. And if I win on that, then I'll yes. If I don't win, I'm okay. Now, if I win on overall survival also, then only I will test for quality of life. Okay. So now you are giving me a hierarchy of the importance of your endpoints. If you start doing that for me, then I'll be able to help you with a smaller sample size. That is what is important for you to understand this concept. You don't have to understand the math behind it, right? But it's important for you to understand this concept of saying that, so if you go to SAR now, you go to somebody else and say, okay, I want this done. Okay, any statistician, they will say, you tell me what is important to you. Are they all equally important, or are some more important than the others? And it doesn't have to be only one of these two. You can say, for example, that I want to win either on PFS or OS. I want either one of these. Okay, then I will say, okay, now instead of splitting an alpha by 3, split it by 2. And once I get one of these two, then I want to go to quality of life. So you can do any combination thereof, and we can help you with that. But you have to give us your needs. Correct. 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 Absolutely correct. Yes. Yeah. I'm here all day today, all day tomorrow. So if you want to do a quick, when you do the protocols or something, if you want to do a quick additional session, I think I can do that. Right. Just one thing, if there is any, okay, no other questions. Thank you. Thank you.